welcome to the Royal Observatory Greenwich, the historical home of British astronomy and a place with a surprising link to this month's topic.
The big story at the moment in our night skies is the fifth planet of the solar system, the mighty Jupiter, and that's what we're going to explore in this programme.
Coming up, physicist Helen Czerski will be trying to uncover some of the mysteries of Jupiter's atmosphere.
The really memorable thing about the Great Red Spot is it's been there for so long.
These features will persist for as long as we keep the experiment running.
Pete Lawrence will be showing us just how easy it is for anyone to get a great view of Jupiter.
We'll be finding out about an astonishing new discovery. Water sprang out from one of Jupiter's moons.
So we're talking about a plume of water 200 kilometres high over the south pole of Europa. And how the pictures you take could be an essential tool in the study of the gas giant.
Jupiter's always a wonderful object to see in the night sky, but right now it's truly spectacular, outshining even the brightest of stars. For the next few months, it will be high in the sky after sunset, making this the best opportunity for British observers to get a look at this fascinating world.
One of the joys of observing Jupiter is seeing those distinctive bands, and of course the red spot. This image shows that in amazing detail. Now, the bands are actually formed by a weather system which goes all the way around Jupiter, with wind speeds greater than 300 miles per hour. And the Great Red Spot is actually 3 times the size of planet Earth and has been raging for over 3 centuries.
And it's to this amazing weather that we turn first. We sent physicist Helen Czerski to see if she could find out what causes this magnificent display.
When you look at an image of Jupiter, the most obvious thing are these fabulous bands of colour that go horizontally across the surface. But Jupiter doesn't really have a surface as such because it's a gas giant. What you see on Jupiter are swirling clouds of many different gases. Effectively what we're looking at are just the tops of complex weather patterns. But what drives this violent and long-lasting weather? You'd think that you can see so much detail, the answer must be obvious. But actually this is one of the biggest mysteries in the solar system. One of the clearest features we can see from Earth is that the atmosphere is arranged in a series of bands circling the planet. These bands are iconic, really strongly associated with Jupiter. But this isn't the only planet to have weather in bands like this. Saturn has clearly defined stripes of light and shade. Neptune also has subtle visible bands. The bands of weather that we're most familiar with are actually here on Earth. It's just that we can't see them because our atmosphere is transparent. But they are there. Earth's atmosphere is actually divided into distinct regions known as cells. Each cell is driven by hot air rising high into the atmosphere and flowing either north or south. There are 6 in total. And the thing that I like about the comparison between Earth and Jupiter is that we can't see those bands, those cells on Earth, but on Jupiter they're really visible. Jupiter has many more cells than we have on Earth. There are at least 12. And that's not just because it's bigger. The number of cells a planet has actually depends on how quickly it's rotating. Earth rotates once every 24 hours. That's what defines a day. But Jupiter rotates roughly once every 10 hours, over twice as fast. And if Earth did the same, our weather would be very different. This is a simulation of the Earth as it is now, looking slightly down from the northern hemisphere, so the planet is rotating this way around. And what the colours represent are wind speeds high up in the atmosphere. But if we change the simulation so we speed up the rotation speed of the Earth by a factor of 4, a 6-hour day, this is what it looks like. And you can see that suddenly there are many more bands stretching around the planet. The winds are constantly being pulled in a lateral direction, and that means it's really hard for currents from the north or the south to form. And so the structure of Jupiter's atmosphere is locked in these bands that we're all so familiar with. The bands of fast-moving winds aren't the only weather we can see on Jupiter. There are also extraordinary vortices and spots, some of which last for centuries. But why do these atmospheric storms last so long? I'm meeting Professor Peter Reid, who's using a jug of water, some sparkling dye and a rotating rig to recreate a section of Jupiter's atmosphere.
Jupiter is quite unlike the Earth in many respects, and in one important respect, and that is that on the Earth the equator is usually hot and the poles are cold. On Jupiter that's not the case, and what we tend to see is that the main temperature differences that we can measure in the atmosphere are actually between the bright bands and the dark bands, so that you will typically have a bright band which is relatively warm, and then to the north and to the south of that there'll be a dark band that is relatively cold.
And that sounds amazing to me, because I'm used to thinking about the Earth, and the idea that the equator is hotter and the poles are cooler is such a strong idea, and that drives all of our weather on this planet. But on Jupiter it's quite different.
And Jupiter has an extra ingredient that the Earth doesn't have, and that is that Jupiter itself is a source of energy from its deep interior. And it actually generates almost as much energy from its deep interior as it receives on average from the Sun.
With this experiment, we're trying to create a simulation of what happens within one of Jupiter's bands. The water is heated, but the edges and the centre of the vessel are cooled. This represents a warm band on Jupiter surrounded by colder air, and then the whole experiment is rotated. After a few minutes, some vortices are created that are so stable they barely appear to move.
So what you can see now is a whole chain of these eddies that are all circulating in the same sense.
So if this was a band on Jupiter, at the bottom of the band the winds are going this way round, and then you've got these eddies spinning like this, but at the top the winds are going the other way.
That's right. So this is just like the bright bands on Jupiter. So to the south the jets will be going in one direction, and to the north they'll be going in the opposite direction, with these vortices rolling in between them.
These rotating storms are trapped within the bands that have been created by Jupiter's fast rotation, and this means they're remarkably stable. On Earth, storms come and go, but on Jupiter, a really memorable thing about the Great Red Spot is it's been there for so long, and these little storms you generated in this experiment are also just persisting.
These features will persist for as long as we keep the experiment running, once the whole thing is settled down.
This is just a two-dimensional representation of what might be happening on Jupiter, but our knowledge doesn't go much beyond that. The problem is that when we look at the planet, all we can see are the tops of the clouds, and it's really difficult to measure what's underneath that. Finding out what's happening deep within the planet is the next great challenge.
Luckily, there's hope that we'll resolve some of these unanswered questions in the near future, because NASA's Juno probe is on its way to Jupiter. It spent the last couple of years wandering around the inner solar system, picking up speed, and at the end of last year, it passed by Earth for its final gravity assist. And remarkably, amateur astronomers were able to image it as it flew past. In this sequence of images from Peter Birtwistle, the moving dot you can see is Juno itself, heading off to Jupiter.
Juno's onboard instrumentation will allow us to peer below the clouds for the first time. It will fly very close to the planet, a mere 5,000 kilometers above the clouds, and below the radiation belt, which has stopped us from taking detailed data in the past. It will take detailed gravitational measurements and measure the atmospheric composition. It will also measure the mass of Jupiter's core, if there is one.
It's an incredibly exciting mission, but we'll have to wait until 2016 for Juno to arrive.
Now, you don't need to travel to Jupiter to get a fantastic image of it. It's possible to capture really detailed pictures of the planet from right here on Earth. And images like these, taken by amateurs, actually provide a unique record that even the space probes can't match. I've been speaking with Professor John Rogers, who gathers these images into a database that scientists can use. How are amateurs helping us understand Jupiter where the professionals can't?
Well, amateurs are able to monitor Jupiter continuously, and its weather systems evolve over timescales from days to months to years to decades. And so we really need continuous observations to work out what's happening.
They're not just doing observations, they're doing some science too.
Yes, well, we can actually compile a record of what's going on, how spots like the Great Red Spot evolve, and we're able to monitor much smaller spots as well. I mean, here, for instance, you see the Great Red Spot. You can also see that the belts are not symmetrical. This dark belt is here, but there's normally a dark belt up here, but on this occasion in 2010 it's disappeared. And so these kind of changes are happening all the time on Jupiter. Sometimes they take many years to unfold, and that's what amateurs can really study.
Actually, I'm not used to seeing Jupiter in this orientation.
Well, this is the way that amateurs most commonly see it, with south up. So the Great Red Spot is in the southern hemisphere, and that's the way we put all our pictures up for display.
But it's not just weather that the amateurs are spotting. They also find impacts. In 1994, the comet Schumacher-Levy 9 crashed into Jupiter, leaving dark scars in its atmosphere. Since then, amateurs have discovered that these kinds of impacts are more common than previously thought.
In 2009, quite unexpectedly, an amateur, Anthony Wesley, discovered such a spot on the planet. This was an image he took 2 nights earlier, and then he saw this remarkably black spot appearing and realized that this might well be an impact. So other amateurs immediately started taking images to confirm, and professional scientists took this image in a far infrared wavelength. The Hubble Space Telescope took this image a few days later. And so the professional astronomers managed to follow this event over several months, while we amateurs were also tracking it over several months.
So the amateurs are the watchkeepers. They keep an eye on Jupiter and then alert the professionals when something really exciting happens.
Yes, indeed. And more recently, amateurs have been noticing impacts while they happen. They're much smaller impacts. They don't leave visible scars, but they're more frequent. And so now 3 times since 2009, amateurs have actually seen fireballs in the atmosphere of Jupiter, which previously, if anyone had seen them, they didn't notice them or didn't believe they were seeing them. But now we have real webcam videos, and it's clear that amateurs are actually detecting flashes as they occur.
So how does an amateur get involved?
Well, the best way for someone who hasn't done it before is to contact their local astronomical society, because there they'll meet people who are themselves getting into the same kind of observations, finding out how to use the same kind of equipment. And I think it's the personal contacts like that that are most useful to someone who hasn't experienced this kind of technology before.
Well, thanks, John. That was truly fascinating, and it shows the power of amateur astronomy.
Well, thank you.
Now, Pete Lawrence is here with his guide to what else you could see in the night sky around Jupiter. But first, he's got a simple tip that can help address one of the main problems that people face when they're stargazing: how to match a star chart to the real night sky. And he's with the Hampshire Astronomical Group on the South Downs.
Now, Jupiter's pretty easy to find at the moment because it's the brightest thing visible in the early evening part of the night sky, apart from when the moon's about, of course. Now, for many people, when they look up at the night sky, it can be a bit of a challenge to work out what is what. But there are a few simple tips you can follow which will make your life easier.
One of the most difficult things for those starting out is judging scale. How do you relate the distance between stars on a star chart to the distance in the night sky? It might sound surprising, but the best thing to do is to use your hands.
If you hold it out at arm's length like that, the distance between your thumb and little finger is the same if you've got big hands or little hands. The length of your arm tends to compensate for it. So if you look at Orion, and you can see the bright star in the upper left corner and the bright star in the lower right corner, you can see that it fits more or less between those two. For all of us, even though we've got different size hands and different length arms, you can actually hold 2 fingers up as well. That's a good indicator. So you're starting to appreciate the scale of patterns in the night sky, and you can relate that back to a star chart, and then gradually work your way across the sky.
Once you understand the apparent distances between stars, finding anything in the sky should be much easier.
Jupiter is obviously the highlight up there at the moment. It's absolutely magnificent, but there's a lot more to be seen around that area, and I've picked out some of my favourite highlights for this month's Star Guide. The magnificent constellation of Orion lies south in the early evening during February. Its 7 bright stars are easy to pick out and create a great signpost in the night sky. Look out in particular for Orion's sword that appears to hang down from the belt, a region which contains the fabulous Orion Nebula. Follow the line made by Orion's belt down and left to locate Sirius, the brightest nighttime star. About 1.5 outstretched hand widths above and left of Sirius is another bright star called Procyon. Join the dots of Sirius, Procyon and orange Betelgeuse to form a pattern known as the Winter Triangle. The Winter Milky Way passes through this region. Scanning the area with a pair of binoculars reveals many faint and beautiful star clusters. Extend a line from Rigel in Orion through Betelgeuse for twice the distance again, that's 2 outstretched hand widths, to arrive at a pair of stars in Gemini known as Castor and Pollux. They're about 3 finger widths apart. If you trace the pattern of the famous twins back towards Orion, you'll find the unmistakably bright planet Jupiter. Now, Jupiter is currently visible more or less all night long, so if you go out and you catch it early, it's possible to see a full rotation of the planet. That's 1 whole day on Jupiter. If you get some lovely pictures of that, send them in to us and we'll put the best ones up on our website.
Speaking of your photos, we've got some great ones that have been uploaded to our website, and here are a few that really stand out. This is the Orion Nebula, which lies on Orion's sword, taken by Steve Richards.
Luke Stacey captured this image of a chain of sunspots on the 2nd of February.
This shot by Mary Spicer shows how light bouncing off the Earth can illuminate the parts of the moon that lie in shadow. And this is Centaurus A, a galaxy that lies too far south to be viewed directly from Britain. It was taken over an astonishing 43 nights by Rolf Olsen.
To send us your images, go to our website at bbc.co.uk/skyatnight. Now, since we were last on air, there's been plenty happening in the astronomical world, and the most spectacular event has been a new supernova.
Yes, but supernova is sort of the dying throes of larger stars, and we have one here captured by some UCL students. So this is the M82 Cigar Galaxy, and here, on the 21st of January, we have a new bright object, the supernova.
What I love about this was this discovery was made by Steve Fossey and a bunch of students just up the road at the UCL's Mill Hill Observatory.
But even better, it was in a 10-minute gap where it wasn't cloudy.
Exactly, so a discovery from within the M25.
And it's perfect because this is a Type 1a supernova, which are quite rare.
That's right, though. We use these to measure how the universe is expanding, so they're bright, so you can see them from a long distance away, and that means we can use them to work out how the universe is accelerating. But embarrassingly, we don't know what they are. We've got some ideas that it might be a massive star spiraling material down onto a white dwarf, which then explodes, but we're not sure, and that's why we need these local ones to try and help us.
Because this is only sort of 12 million light years away, which is pretty local.
It's just round the corner.
Yes. Is it still visible now, or does it decay very rapidly?
Well, it'll be visible for the next few months, and actually it was caught early enough that it was still brightening, and so it'll be at its brightest about now. So you could go out, find M82, and if you look in binoculars, you should see it easily. Won't quite make it to naked eye visibility unless something odd happens, but it'll be an easy target in binoculars, and the brightest supernova we've had in the northern hemisphere for years. Now, speaking of celestial spectaculars, we had hoped before Christmas that Comet Ison was going to put on a great show for us, but it didn't quite work out like that, and Alan Fitzsimmons is going to tell us why.
People were predicting that Ison would be the comet of the century. That as it came round the sun, a huge tail would be created that would fill the night sky. However, instead, it seems to have fizzled out. But now, by pooling data from a number of scientific instruments, it's possible to find out what actually happened.
Here we've got the comet about a couple of hours before closest approach to the Sun. And we can already see that something has happened to the comet, because in a normal comet we expect to see a very bright distinct head or coma formed from all the gas and small dust particles that the comet has released. Here we can see the tail of the comet, but the head itself is already not looking like a normal comet does. It's spread out, and we believe that even by this point, a couple of hours before it reached its closest point to the Sun, the comet nucleus itself had been dispersed. Now, interestingly, it's still far enough from the Sun that it shouldn't have been broken up by the gravitational field, the tidal forces imparted on the nucleus by the Sun. But what's happened is simply the nucleus has been heated so much and it's releasing so much gas and material from its surface that that pressure of that material building up in the comet has simply broken it apart.
And so ISON was doomed long before it reached the Sun, and as it passed around our star, it reappeared as nothing more than a cloud of debris. But there was still a question about whether anything in the nucleus had survived to live another day.
On December the 16th, the Hubble Space Telescope went to have a look at where the comet was predicted to be. Now, it's tracking where we expect the comet to be moving, so all the background stars and galaxies appear as streaks. But if there was any comet left, we would see it as a point-like source here, and we don't see anything. So these Hubble telescope images here imply that there really isn't anything left at all of the nucleus. So it's a shame. ISON is gone, but it gave us a great show on its way in.
And we've got one more item of news this month.
In January, as part of Stargazing Live, I challenged people to go online and look at pictures of galaxies and look for gravitational lenses, places where a distant galaxy has had its light bent by a gravitational lens by passing near a nearby galaxy. We found lots of spectacular things, but the one we talked about on the night was this one. This is an infrared image of that galaxy.
Yes. So what have we got? In the centre, that's the galaxy.
That's the nearby galaxy,
Lovely.
and then the red arc that you can see, almost the red ring, there is a distant galaxy whose light has been bent, and we're seeing it because it's being lensed by this nearby galaxy.
So without that galaxy, we wouldn't have a chance of seeing it.
Right, exactly. It's nature's telescope, but this is the infrared. What we've been doing since is we've looked at it in the radio using Jodrell, and this is the image that we've got.
But it does look quite different.
It does. For starters, it's blobby because it's a radio image and you don't quite get the beautiful pictures you do in the infrared. But the other thing, I don't know if I can convince you of this, but in the infrared we saw that red ring. In the radio, it's only one arc, one side.
Actually, yes, it does definitely look one-sided. So where's the rest of it gone?
Well, exactly. It's quite confusing, and our best guess at the minute is that the radio and the infrared radiation come from different parts of the galaxy. So the infrared comes from star formation, spread out through the whole galaxy, and the galaxy's forming stars at a great rate, about 100 times that of the Milky Way. And the radio, we think, comes from right in the centre, from the nucleus, where material's spiralling onto what must be a growing black hole in the centre of this galaxy.
This is what I love. Looking at the sky in different bands of the electromagnetic spectrum gives you very different viewpoints and different understandings.
That's right, and we knew that was true, but I think it's only the second time that we've seen this misalignment between a radio lens and an infrared lens. So perfect ring in the infrared and a nice blobby arc in the radio. It's quite fun. If you go to the Sky at Night website, we've actually put some more data online. If you follow the link, you might be able to discover your own lensed galaxy. Well, back to Jupiter, and we're in the Endeavour room of the Royal Observatory Greenwich, which these days is a library, but which used to house some of the largest telescopes on the site. It was in this room in 1908 that British astronomer Philippe Melotte discovered a moon of Jupiter. And this is the image, and this dot here is the moon we now call Pasiphae. And exciting things are happening with the moons of Jupiter, and to discuss them, I'm joined by Dr. Lee Fletcher, an expert on the Jupiter system. Lee, welcome to the program.
Thank you.
We're going to talk about Europa, where jets of water have been discovered shooting into space, but we knew there was water on Europa already.
We did. I mean, Europa has always been a tantalising place for us to one day go and explore, and now more so with this new result of plumes of water vapour being emitted from the south pole of Europa, it's going to be a fabulous thing for us to go and look at one day.
So Europa's an icy moon, and that's what we see when we look at the surface.
Yeah, Europa is the second of 4 Galilean satellites in orbit around Jupiter. It's about the size of our own moon. If you look at it here on the screen, you can see that it's an icy ball, Europa is. And the different colours that you see across the surface are contaminants in the ice itself. And it almost looks like you've got frozen ice rafts frozen then into a body of liquid water that is refrozen. So we call it chaos terrain.
We can zoom in, I think, and get a proper look. Yeah, there we go.
And this is one of the key pieces of evidence which suggests that beneath this terrain there's liquid water. Liquid water in our solar system locks away beneath the icy surface.
But we've been talking about this for years, and there's this annoying catch, isn't there, that the ice is actually pretty thick.
This is the typical thing within our solar system of the ability to sense what we really want to see, which is that ocean, is forbidden to us because it's hidden away, locked away. Or so we thought. But now, with the discovery of these water vapour plumes, we have a tantalising chance to fly through those plumes and sniff out composition.
Well, let's look at that new observation. So this was released at the end of last year. It's a Hubble Space Telescope observation. And I have to say, Lee, look at this, it's not hugely convincing.
Well, I'm very sorry that you're disappointed, but this is actually a really exciting discovery that the folks with the Hubble Space Telescope made just a little while ago. Now, don't forget that you're seeing this from planet Earth, 5 astronomical units away.
5 times as far away from the Sun as the Earth is.
Absolutely, all the way out at the orbit of Jupiter. This is an artist's impression superimposing the two things together. What they're looking at here is ultraviolet emission from hydrogen and oxygen. So this is water that's been spewed out of the moon and has then been dissociated, split apart.
Just by the sun's light.
Exactly, by UV radiation. And we can see that emanating from the South Pole. So we're talking about a plume of water 200 kilometres high over the South Pole of Europa. And I can tell you we didn't expect to see that.
So how have we got water at the South Pole?
Well, what's going on here is we've got these cracks and these fissures and stripes which are undergoing different amounts of stress as the moon goes round Jupiter. Now, the orbit of Europa around Jupiter is not perfectly circular, and that means sometimes it's closer to Jupiter where the gravity is stronger, and sometimes it's further away from Jupiter where the gravity is weaker.
Jupiter's a big thing. Its pull is pretty significant.
It's an immense gravitational field, and that means that when Europa is far away from the moon,
like this observation
in December 2012, things are relaxed, you're able to emanate these plumes out of the South Pole. Now, the team also have observations from just a month earlier. At that point, Europa was much closer into Jupiter, so where the gravity field is stronger, if you like, and no plumes were observed at that point. So you have this situation extremely dynamically rich, where the plumes are only emanating their material into space when the stress is at its lowest point at the furthest distance away from Jupiter.
Now, this is a fabulously exciting discovery. It provides access to this water, the stuff we thought was locked up under the surface. And you have a mission, or you're part of a team working on a mission called JUICE, which is heading to Europa. So how does this change your plans?
It's being built by the European Space Agency to launch in 2022 or thereabouts. And at the moment, we're scheduled to have 2 flybys of Europa in 2031. We're going to be up close and personal with those plumes, able to look at the light as it's being filtered and scattered through them. We've even got instruments on board capable of detecting the sorts of materials that are emanating. Now, there's a huge caveat to that, I should say. What if this material isn't coming from the ocean? Maybe it's the action of something heating up in just the very top layers. Even then, it's still exciting because it's a way we can sample the surface materials from our spacecraft without landing on the surface.
So when does JUICE get there?
JUICE will get there in 2030, and it will fly by Europa twice in 2031.
Well, fabulous. Well, come back and tell us about it, and good luck with the mission.
Thank you very much.
Lee, thanks a lot.
Thank you.
So that's it for this month, but do remember to keep on sending your pictures in, especially if you manage to get a full rotation of Jupiter, and we'll put the best on our website.
When we come back next month, we'll be listening to the cosmos, studying sound waves to find out what they can tell us about the universe's hidden secrets.
And we'll also be looking at how to get wonderful images of the night sky with just a smartphone. So remember, get outside and get looking up.
Good night.
International drama tonight here on BBC4. A young girl settling into a new neighbourhood introduces herself as a boy and begins a confused double life. Turned French film Tomboy is this week's world movie premiere. Next.